Okay, let's take a look at exponential, logarithmic, and hyperbolic functions. A deeper look, I should say, because all of these functions were covered in Calc 1 in their what are they, how do we work with them, and how do we find their derivatives. In this section, though, we're going to go a little deeper into all of that as well as looking at their integrals. Now, if you are hearing me say hyperbolic functions and this is a type of function you have not explored, your Calc 1 course did not explore that, I have included the intro to hyperbolics as well as derivatives and some proofs and identities and all that good stuff from Calc 1. I have included that in the Canvas content if needed for review. Please do check that out. Okay, so I've also included this table of useful facts. And notice there's a lot of blanks on here because this is for you to use and for you to fill out. So the first column, so over here in this column, or these two columns, I should say, are some basic functions. We've got our exponentials, our logarithmic, and our hyperbolics, all six of the hyperbolics and three of the inverse hyperbolics. And you should be able to write all of their derivatives down. So as a little review, you should go through this on your own in its blank form and fill in that first column. And then you should also be able to take those derivative formulas and certainly through our exponentials and logarithmics, we've actually been already working with those. So you should easily be able to fill in those integrals and then take what we now know about the derivatives of the hyperbolics and the inverse hyperbolics and come up with the corresponding integration formulas. Now, these last four down here are going to involve a little bit of U sub. So if you want to, those are great practice problems for some U sub, working with both the hyperbolics and the U sub. So please give this sheet a try on your own. I'm going to go ahead and project the solutions right now, but this would be a good time to pause the video and just say, hey, where am I at coming into this chapter? And run through this sheet and see if you can fill it out. Again, I'm projecting this sheet on the video. It is also in the module and on the page where you found this video. So you can find this sheet in lots of ways, or you could even just copy down these formulas in your notes right now and take the derivatives. Okay, one other thing that is also on this sheet are just our basic hyperbolic definitions of all the hyperbolic functions, as well as the first three hyperbolic identities. Just like with the trig functions, these hyperbolic functions have a whole slew of identities, but these are the basic hyperbolic identities, how they're connected to that unit hyperbola. And here are the inverse hyperbolic functions in their logarithmic forms. And then, of course, just a funny little cartoon there that I put on this sheet to hopefully by the time you get to the bottom of it, give you a little chuckle. All right, so I paused the video there for a second and now I've filled in that sheet and hopefully you have as well. And so those are all of our formulas for our exponential, logarithmic, hyperbolic, and three of the inverse hyperbolic functions, both their derivative formulas and then their corresponding integral formulas. Now, again, those last three, as I mentioned, and that's what that little star is down there at the bottom, those last three can be proven using the formulas from above and a nice little U sub. So that's kind of a nice extension off of the basics, if you want to say that, and give that a try. I did want to go through one of these though, because it's a nice little proof and it's kind of setting us up for working with these functions. And so let's take a look real quick at where does this formula come from? Because that is a little beyond what I would say beyond the basics of the hyperbolic integral. So it's not just a basic conversion from a derivative formula to an integral formula, but it doesn't take much to show that that proof is true. So I've hidden the proof, or I've hidden the formula so that we can actually prove it real quick. So to prove that the integral of the hyperbolic tangent of x is what it is, what we're going to do is rewrite it in its sinh and cosh form. So the hyperbolic tangent is the hyperbolic sine over the hyperbolic cosine. And we can do a quick little U sub. If we let u equal the hyperbolic cosine of x, then the derivative du dx is the hyperbolic sine of x. But we'll separate the differential and write that as sinh of x dx. I'm using that terminology because we can call the hyperbolic sine sinh, and so that is just kind of shorthand for hyperbolic sine. I'm going to make those substitutions. This becomes 1 over u du when I make the substitutions. And we know, of course, that that's the natural log of the absolute value of u plus c, which is the absolute value of cosh, since our u was cosh, hyperbolic cosine, plus c. But the hyperbolic cosine is always positive. So since the hyperbolic cosine of x is actually always greater than or equal to 1, so since it's always positive, we can even drop the absolute value signs, and we can show that the integral of the hyperbolic tangent is the natural log of the hyperbolic cosine plus c. And that's a nice little proof using one of our basic integral strategies, our u substitution, and what we know about integrals of 1 over u and hyperbolics. And there's just a lot contained in that simple little proof, but that is one of the ones that we'll start with as a example of working with hyperbolics, exponentials, and logarithms. So made that little star, but that's where that proof comes from. And that formula does show up here in our basic table of useful facts. So again, I'll go ahead and I will project that table up there on the screen. And if you haven't already done that on your own, make sure you do get that filled in on that reference sheet, because that will be a useful sheet as we're working through these problems.